Okay, so let's go to the February-March 2022 papers that I just gave to you guys. All right, so this one we'll consider as something like a revision of the entire syllabus, and then from there we can identify whether do you have any big problems with certain chapters. Okay, so February-March 2022, a sphere of radius 2.1 millimeters fall with terminal constant velocity through a liquid as shown in figure 1.1. Three forces act on the moving sphere. The weight of the sphere is 7.2 times 10 power minus 4 Newton, and the upthrust acting on it is 4.8 times 10 power 4 Newton. The viscous force acting on the sphere is given by Fv equals to KRV, where R is the radius of the sphere, V is the velocity, and K is a constant. The value of K in SI units is 17. Now determine the SI base units of K. All right. So if you let's say you have a rough piece of paper right now, we can actually just do this together right now, and then you check whether your answers correspond with what I write here. They want you to find out the SI base units of K. Your K is over here. So usually when it comes to questions like this, when you want to find out the unit of some particular quantity, it's often best to make that quantity the subject first, because it will make your life easier. So if Fv is KRV, unit of K is unit of the viscous drag divided by unit of RV. Okay, maybe I write it like this. All right. K is Fv over RV over RV. So unit of K is unit of viscous drag over unit of RV. Okay. So we know that unit of force is kg meter per second squared, because force is MA, right? So unit of force is unit of MA. So it's kg meter per second squared. So unit of force I know is kg meter per second squared. And then the unit of R, what is R here? R is the radius, so it will be meter. Then V is the velocity, so it will be meter per second. So all you just need to do from here is to simplify it. Meter and meter will cancel off. Then second power -2, power -2 minus with -1. Eventually you will get the answer is kg per meter second -1. And this one should have been the answer for this. So we just go through this one. Let's just check from there. Your answer will be kg. Yeah, kg per meter per second. Okay, right. So this one, no issues here. Then after that, we move to the next part. Because they want SI base units, always ensure that it is in base units, all right? Because sometimes some people may accidentally write force as Newton. Newton is SI unit, but it's a special SI unit for force. Since the question wants base unit, you cannot write Newton. You must write it as kg meter per second squared. Okay, so be mindful of that. They want it in base units. Okay, so from here, use the value of upthrust acting on the sphere to calculate the density rho of the liquid. Use value of upthrust acting on the sphere to calculate the density rho of the liquid. Okay. Value of upthrust to calculate the density rho of the liquid. So did they give you your upthrust? Let's just see from here. The weight and the upthrust, yes, they told you the upthrust acting on the liquid, acting on the sphere is 4.8 times 10 power minus 4. Okay, so you see keyword here, upthrust is 4.8 times 10 power minus 4. So they say use the value of upthrust acting on the sphere to calculate the density rho of the liquid. All right, now for this one here, when it concerns upthrust, the first thing that you guys should have the first thing that should come to your mind is that upthrust is equals to the weight of liquid displaced. Okay, this is what upthrust actually is. It is the weight of liquid displaced, which in turn can be written as rho Vg. Okay, so this one is your weight of liquid displaced. So from here, they want you to actually calculate out the density rho of the liquid. So bear in mind that this rho is the density of the liquid. This V is the volume displaced, volume of liquid displaced, which so happens to be the volume of the sphere. Okay, then G is just G lor. All right. So right now they want you to find the density rho of the liquid. They want you to find this. So given that upthrust is 4.8 times 10 power minus 4, 4.8 times 10 power minus 4, your rho is this. Your volume, you know this is a sphere. Okay. So did they give you your radius also? Yes, they did give you your radius. So volume of a sphere is 4/3 r cubed times g. Right. So maybe I write it like this now. Upthrust is rho times 4/3 r cubed g. Then you start subbing in the values. 4.8 times 10 power minus 4 rho 4/3 times with your radius. It's 2.1 times 10 power minus 3. So you cube it and then you multiply with 9.81. So your rho, if you do it properly, you can also try to calculate out and then check your answers with mine. 4.8 times 10 power minus 4 times 3 divided by 4 divided by 2.1 times 10 power minus 3. Remember to cube, then divided by 9.81. You should be getting the values as 3.96 times 10 power 3 kg per meter cube. Okay, this one is very, very dense, but let's check the answer. Hey, I got
1.3 pi.
Sorry? Yeah, you got 1.35, right? Wait.
No,
Yeah.
isn't volume pi 4/3 pi r cube?
Volume, wait, 4/volume of sphere of pi, sorry. I forgot the pi. 4/3 pi r cube, right? Okay, sorry. 4/3 pi r cube. Yeah, sorry, I forgot the pi there. So if you go and put this one in, 4.8 times 10 power minus 4, 10 power minus 4 times 3, divided 4 divided by pi divided by 2.1 10 power minus 3 cube divided by 9.81. You're going to get 1.26 times 10 power 3 kg per meter cube. Is this the answer that you all got? Right? Now this one is in 3SF. Okay. So this one, I write the answer in 3SF. If I were to change this to 2SF, the answer will be 1.3 times 10 power 3 kg per meter cube. This one is if I write it in 2SF. Okay. Your marking scheme answer nowadays, they will always write it in 2SF. Okay. So while you do your question, sometimes you will notice that how come your value is like this, but then your answer in the marking scheme is seemingly different. It's mainly due to the fact that your final answer is always rounded to 2SF in the marking scheme. Okay, so you can write your answers as 3SF, you can write your answer as 2SF. I think I mentioned this to you guys before. Final answer is minimum 2SF, maximum 3SF. Okay, Don't go any less, don't go any more. Unless the question specifically tell you to do otherwise. So that's one thing to note here. Right, so your uptrust is that. This is worth 3 marks. The previous one was worth 2 marks. Then you look at the next one. On the sphere in figure 1.1, draw 3 arrows to show the directions of weight W, upthrust U, and viscous force FV. Okay, label these arrows U and FV respectively. Okay, so this one is a no-brainer. This one should be quite easily doable. Your weight should be acting downwards. This is W. Your upthrust should be acting outwards, U. Your viscous drag. Okay, your viscous drag is something that you guys need to be a bit careful of. Now, upthrust is always upwards. Weight is always downwards. But viscous drag, FV, this one you need to be careful of it. Viscous drag always opposes direction of motion. Okay, so what I mean by that is that if let's just say your object is falling down, this is the direction of your motion, your FV would be upwards. But if let's just say your object was actually trying to float up and is moving up like this is your direction of motion, your FV will be downwards. Okay, so just be careful a bit when it comes to viscous drag, or rather they call it drag force now. Okay, drag force is the same as viscous drag. It always opposes the direction of your motion. It can be up, it can be down, depending on how your object was moving in the first place. So in my case here, one of the things that I want to find out is whether was this object moving up or moving down in the first place. So one way to look at it would be to look at the question. Notice that they told you that it is constant velocity downwards. So this one, I know my motion is downwards. So my viscous drag therefore must be opposing my motion. I would have FV. So this one is here. Okay, this one opposes your motion. Okay, so simple as that. And then you get your 1 mark already. Okay, then from here, determine the magnitude of the terminal constant velocity of the sphere. Okay, so this one here kind of relates to another separate part of your chapter. They ask you to determine the terminal velocity of the sphere. Now, one of the main things that you've learned for terminal velocity was that, let me just write off whatever you have here. When you have terminal velocity, your net force is 0. So right now, you've actually already gotten this thing here over here like this. Your forces acting on the sphere just now from the previous part of the question. If your net force is 0, and you know that these were the forces acting on the sphere as it was dropping, you ought to be able to work out an equation from here. So net force is 0. You can just think of it as outward force is equals to downward force. So in my case, I would say U plus FV equals to W. Now from here, they want the velocity, right? So you have to make use of something that has velocity inside. Your equation that you just wrote, you have to substitute one of the things so that you have an expression for velocity. And it so happens that they already gave you that. Your viscous drag is actually FV equals to KRV. So from here, I know this one is going to be U plus KRV equals to W, right? So from here, you also know all the other relevant values already. Your upthrust is 4.8 times 10 power minus 4. Your value of K, the question already told you, is 17. They say already in SI units, so you don't really need to bother about the units because you're working with SI units throughout your equation here. All right, this is 17. Your radius is 2.1 millimeter, so it's 2.1 times 10 power minus 3, then multiply with it. Okay, then your weight is also already stated as 7.2 times 10 power minus 4. So this is 7.2 times 10 power minus 4. Now you already have the whole complete picture here from which you can find out what is your V. Okay, so let's just quickly calculate it out. So you have 7.2 times 10 power minus 4 minus 4.8 times 10 power minus 4 divided by 17 divided by 2.1 divided by 10 power minus 3. You should have 6.72 times 10 power minus 3 meter per second. Okay, that is what you ought to get, but let's check the answer. Yes, you get 6.7 times 10 power minus 3 meter per second. Okay, so the answer was here. Right, so 6.7 times 10 power 3 meter per second. If I were to change my answer from 3SF to 2SF, I'm actually getting that same answer. Okay, right? So this one is for question 1. So far, so good, I hope. Right, so this one is okay. Then after that, I move on to the second question. This one is about your kinematics. All right, so I'll clear off everything that we have here. Now you have water that leaves the end of a hose pipe at point P with a horizontal velocity of 6.6 meters per second, as shown in figure 2.1. Point P is at a height h above the ground. The water hits the ground at point Q. The horizontal distance from P to Q is 3.5 meters. Air resistance is negligible. Okay. Assume that the water between P and Q consists of non-interacting droplets of water, and the only force acting on each droplet is only its weight. Okay, so this part is kind of important. The only force acting on the droplet is only its weight. Now, explain briefly why the horizontal component of velocity of a droplet remains constant as it moves from P to Q. Okay, so why is it that your velocity of water droplet, specifically the horizontal component of velocity of your water droplets, remains constant? Now, when it comes, this one is actually your kinematics question, all right? So if I just consider, let me just zoom in for a while. If I just consider one droplet of water, okay, one droplet of water is moving along this path here like this. So I can consider a few points along the path of motion of that water droplet. Usually when you have anything that moves in a curve like this, you are supposed to analyze the motion in two components, horizontally and vertically. This is the main thing that you will have learned in kinematics. Now, one important thing to know here is this. They tell you air resistance is negligible. Okay, this one, they tell you air resistance is negligible. So from here, this one automatically, a lot of times the moment you see this, you can actually make one conclusion already. You will have constant horizontal velocity. And then you have constant vertical acceleration. Okay, these are the two main things that normally come when air resistance is negligible. So why do you have constant horizontal velocity is because no force, no resultant force acting horizontally. Therefore, according to Newton's first law, the velocity, the horizontal velocity remains constant. Okay, Newton's first law, you guys would have learned before. It tells you that an object remains in the state of motion unless an external resultant force acts on it. Meaning to say, if something is stationary, it will remain stationary unless a resultant force acts on it. Or if that object is really moving with a certain velocity of say 6.6 meters per second, in the absence of any resultant force acting horizontally, that object will continue to move with 6.6 meters per second throughout. That is the conclusion from here. Okay. The moment you see air resistance is negligible, this is most of the time the conclusion that you will get. You will have constant horizontal velocity. No, because no horizontal force acting horizontally. There's no air resistance to oppose your motion horizontally. There's no other force to oppose your motion horizontally. So I can say this. So then from Newton's first law, I would say that your horizontal velocity remains constant. Okay. But then after that, why do I say that you have constant vertical acceleration? Okay. So when you have constant vertical acceleration, the one thing that will come to mind, the reason why you have constant vertical acceleration is because weight is the only force acting. And it is your resultant force it is the resultant force. Okay. So since weight did not change, since the weight remains constant, when your object falls down, the weight doesn't change. Since weight remains constant, F net remains constant. So F net remains constant. Therefore, acceleration remains constant. So throughout this motion here, when your object is falling, I know that you have weight W. The question already told you you have weight W only over here. The only force acting on each droplet is the weight. So the only force is just the weight. So the weight itself is your resultant force. And since the weight doesn't change, your net force doesn't change. That net force doesn't change. Your acceleration therefore remains constant. Then one thing I should probably mention to you here is that this one is something that is good to remember. If the only force acting on a falling object is just the weight, the acceleration is always g equals to 9.81 meters per second squared, regardless of their mass. Okay. So this one is one thing that is useful to know from your kinematics. The moment you see any falling object and you see that it's only the weight, you can just automatically assume that the acceleration that it experiences is g, regardless of whatever mass they have. I can tell you I have a 1 kg mass. I can tell you I have a 100 kg mass. This one has weight W1, this one has weight W2. If I say that these are the only forces acting on the falling object, no air resistance whatsoever, they both will experience an acceleration equal to g, regardless of the mass. Okay, this is the main take-off point here. So now back to part A lah. Explain briefly why the horizontal component of velocity of droplet of water remains constant as it moves from P to Q. Just now this one I explained, right? You don't have any forces horizontally. So according to Newton's third law, it will remain constant. So here was your answer. Force on droplet of water in horizontal direction is 0. You can somehow say this also, no resultant force in the horizontal direction. Therefore, the object remains at constant velocity. Maybe I better write it out. No? Okay. No resultant horizontal force. Therefore, droplet continues at constant velocity horizontally according to Newton's first law. Okay, this is something like a full answer to really understand what's happening. No resultant horizontal force, therefore droplet continues at constant velocity horizontally according to Newton's first law. Okay, so this one is for this one. Okay, then from there, we move on to B. Show that the time taken for the droplet of water to move from P to Q is 0.53 seconds. Okay, this one also has some important thing to note here. This one is kind of like, yeah, this one is something I want to also kind of highlight to you. Now, when your object was, say your droplet of water was moving from P to Q, the actual path that it took was the green colored highlighted path here, okay? The actual path that your droplet took was this green highlighted path here, okay? But when you try to split out the motion into two components, both the horizontal and vertical component, if you were to move from P to Q, it actually consisted of two separate motions. The first motion is you moving horizontally like this. And then the second motion was you moving vertically downwards like this. Okay, these are the two motions. For you to move from P to Q along this parabolic path, you can actually think of it as consisting of two motions. You moving number one horizontally and then number two vertically. So the important thing to note from here is that if say it for this path here, it took me 5 seconds. For the horizontal component of the motion, it will also be 5 seconds. For the vertical component of motion, it will also be 5 seconds. So an important thing to note from here is basically this. This one, I think I wrote it in my kinematics notes before. Just always remember this now. Time to move horizontally to a point is equal to time to move vertically to the same point. Okay. If I tell you you move horizontally from here to here, it took you 5 seconds. Vertically from here to here, it will also be 5 seconds. Okay. And also likewise, if you consider the entire motion itself, it will also be 5 seconds. Okay, you won't have different times. They will all be moving at exactly the same time. So show that the time taken for the droplet of water to move from P to Q is 0.53 seconds. So if you want to consider what is the time that it took to move from P to Q, here to here like this, you can actually just consider either the horizontal or vertical motion and find the time. That time will be the same as the time to move from P to Q itself. Okay. So in your case, you will probably have an easier time considering the vertical motion. Usually we will take the vertical motion. So if you consider the vertical motion, I know that I want time. You can actually use S is ut plus half at squared. I'm moving downwards, so my sign convention is downwards positive. Now, whenever you use kinematics equation to find something, you will always notice, I'm not sure how you guys learn it in Charterhouse. For my case, usually when I want to use kinematics equation, I will always assume a sign convention. Sign convention is which direction is assumed to be positive. In my case, my sign convention is downwards positive. Sign convention always follows initial direction of motion. That is how I always do my sign convention. If the thing was moving down, my sign convention is downwards positive. If the thing was moving up initially, my sign convention is upwards positive. Okay. Some of you may not have used the term sign convention. Some of you learn it differently. So I'm not too sure about that one yet, but I'll just show you how I do mine usually. So downwards is positive for me. Okay, this is downwards positive for me. Then after that, if we want to do this, I actually can't do this because I have some issues here, right? You see, this one I can't do because I do not know what is the vertical displacement. I know my initial vertical velocity is 0. And then after that, my A is actually my G. Okay, it's 9.81 and then T squared. Now you see, if I do it like this one I'll get stuck already. This one is 0. My T is 0. This is definitely wrong already. Okay, this one is if I consider vertical motion. If I try to solve it using vertical motion, I'm going to get stuck here already. Because in the first place, I did not know what is my value of H. If I know my value of H, I can solve this one straight and find out the value of T. So this one is out. So if I cannot use vertical, why not I use horizontal? Okay, this one, the one that I wrote here, this one cannot use, cannot pakai. Okay, let's just say I use horizontal. Now for horizontal, I can use Vs equals to Sx over T. The x here is just determining the horizontal component. So Vx is Sx over T. Now this one I can use because you see, I know my component of velocity horizontally, which is 6.6. I also know my horizontal displacement, which is 3.5. So this one is something that I want to use actually. So I would use 6.6 equals to 3.5 divided by T. So T is actually 0.53 seconds. So this is shown. Okay. So I cannot use vertical motion here because I will get stuck. All right. Even if I try to use the other kinematics equation, you will eventually find out there's not enough information for you to work with. It will be better for you to consider just the horizontal component. And besides, you see, this is just one mark. Your working is not supposed to be that long. Okay. Right. So here you use the horizontal one to do. Now from here, you look at part C, they ask you to calculate height h now. Okay, now height h now, you are considering the vertical component of motion, definitely. So this one, you will use your kinematics equation. Use kinematics equation for vertical motion. I already know I have constant vertical acceleration, so therefore kinematics equation would always apply here. So now I want h, my h is actually my displacement. So from here, I will actually use that same equation that I used just now. S is equals to ut plus half at squared So again, my sign convention is downwards positive because my object moved downwards first. My initial vertical velocity is 0. My g is acting downwards, 9.81 meter per second squared. It's in the same direction as my sign convention, so this one will be 9.81. Now my time, I will use 0.53 second squared. Okay, you see this time that I use is the same as the time that I found previously. Okay, just now I mentioned to you the time that it took for you to move horizontally to one point is the same as the time to you to move vertically to that same point. It's the same time. They will always share the same time if you're sharing the same point. Okay, if you're sharing the same point, you will always share the same time. So in my case, I already found from the horizontal motion 0.53. I'm going to use it for my vertical motion too. So this one, I just sub everything in. I'll get 0.5 times 9.81 times 0.53 squared. You're going to get an answer as 1.38 meter. Okay, so this is your answer. Okay, let's just check the answer. Yeah, time taken 3.5 divided by 6.6 equals 0.53. Then after that, you use s equals to ut plus half at squared. You're going to get 1.4 meter. This is in 2SF. At 3SF is 1.38 meter. Okay, so you're going to get the answer here. Simple as that. Now, then after that, you move on to the next one. Okay, so this one, okay. I'll just illustrate to you some important things. Okay, so if you look at the next page, they are asking you for movement of droplet of water from P to Q, state and explain whether the displacement of your droplet is going to be less than, more than, or same as distance along its path. Okay, so the keyword here is you need to identify the difference between displacement and distance along its path. So let me just draw back to you that little thing from earlier. This one is your water coming out, right? This is your water coming. Yeah, this one is your water coming out. Okay. I know that this one is P, this one is Q. When they say distance along its path is referring to this. Okay, this one is the distance along its path, right? So what is the difference between this distance along its path with displacement? Displacement is actually this one here. Okay. We all know displacement is this one, right? So this one here is displacement. Now, displacement may be defined as distance from a reference point in a specific direction. This one was the definition that I wrote in my notes. Displacement is distance from a reference point in a specific direction. Distance from reference point in a specific direction. This is the common term they use in your marking scheme when they ask you to define displacement. But you can also think of displacement as this. Displacement is straight line distance between 2 points. Sometimes you also say as the shortest distance between 2 points. Okay, these two aren't really used in your, they aren't formally used in your exam marking scheme when it comes to definition of displacement. The ones that is formally used is the first one here, distance from a reference point in a specific direction. Number 2 and number 3 here is another way of interpreting what is displacement. It is actually straight line distance between 2 points. It's also the shortest distance between 2 points. The shortest distance between any 2 points is always a straight line. So they're actually kind of referring to the same thing. Okay. You can say it's a straight line distance between 2 points. You can say it's the shortest distance between 2 points. They actually mean the same thing. This one is the easier way to understand what displacement is. But when it comes to defining what is displacement, displacement is actually distance from a reference point in a specific direction. So right now, just by looking at the diagram that I just drew here, is your displacement going to be less than, more than, or same as? I mean, just by looking at the geometry of this thing, you can actually say that your displacement is going to be less than the distance along the path, right? Okay. Because of this, here they start to use this one already. They start to use point number 2 or point number 3. They say displacement is straight line distance or minimum distance from P to Q. So it's going to be less than the distance along the path. All right. Displacement is straight line distance or minimum distance from P to Q. So it's less than distance along the path. Now you see the guidance here, the examiner's report, the guidance here, the notes here for the examiner, they say, if you say the displacement is distance from a specified, is the distance in a specified direction, therefore less, then also allow it. Okay, this one is relating to your first definition. If you say displacement is the distance in a specified direction, therefore it's going to be less, they will also accept it. But then this one, you may not really understand. I mean, just by reading it as it isn't really that clear why is it less. Unless you're using the second or third meaning, then this one becomes really clear why is it less. So either way, they will allow any one of them, okay? Just use either one. Okay, so that one is all right. Then after that, I will ask you to find out what is the magnitude of the displacement. Calculate the magnitude of the displacement of a droplet of water that moves from P to Q. Okay, so calculate the magnitude of the displacement of droplet of water that moves from P to Q. They want you to calculate this magnitude. So this one, just now earlier I mentioned to you, for you to move from P to Q, it actually involves you moving a horizontal distance and a vertical distance, an SX and an SY. So the combination of these two motions will give you this one here, right? Okay. So if you know what is your horizontal displacement and your vertical displacement, these two will actually form a right angle triangle with displacement being your hypotenuse. So your displacement can actually be square root of sx squared plus sy squared. You already know sx squared as 3.5 squared. You already just found it earlier. This is 3.5. Your sy is actually your h. Okay, your sy is actually your h just now that you found. Just now I found it as 1 point something. Okay, I used the marking scheme answer 1.4. I forgot what was my earlier answer, 1.3 something. I'll use the marking scheme one. So you get 3.5 square plus 1.4 square root. You're going to get 3.77 meter. So this is your displacement. Okay, right? So again, round it up to 2SF, you're going to get your answer as 3.8. Right, so this one, okay. This is your kinematics. So far, so good. All right, so I move on to the next one. Okay, so this one is already a quarter of the paper done. Okay, this one is momentum. Okay, so this one is another thing. Okay, now a jet of water hits a vertical wall at right angles as shown in figure 3.1. You have horizontal jet of water with density 1000 kg per meter cube. Your cross-sectional area is this value, velocity is this, you have your vertical wall, and then your water runs down the wall. Water hits the vertical wall with velocity 5 meters per second in a horizontal direction. The cross-sectional area of the jet is 1.5 times 10 power minus 4 meters squared. The density of water is 1000 kg per meter cube. Water runs down the wall after hitting it. Show that over a time 1.6 seconds, the mass of water hitting the wall is 1.2 kg. Show that the mass of water hitting the wall is 1.2. Okay, right. You want to show that the mass of water hitting the wall is 1.2 kg. You can consider, say, this volume here. Now, you know density is mass over volume, such that mass is rho v. So here, what you want to do is you want to do this. Mass is density times volume. This one is a cylinder, okay? So your volume is actually the area times with the length, okay? Now, how do I know what is this length L? This is my length L, right? Bring this one here is my cross-sectional area. While I do not know what is the length itself, I can actually calculate it out given the velocity and time. This length L is actually velocity times time, because we know that velocity is length over time, right? So length is Vt. So this one can be re-expressed as density area Vt. And then from here, you can actually just straight away find out your values. No? So this is 1,000. Cross-sectional area is 1.5 times 10 power minus 4. Velocity is 5. Time is 1.6. And you get your answer already by right. Times 5 times 1.6. You're going to get 1.2 kg. So this one is shown. Okay. Then after that, from B, calculate the decrease in horizontal momentum of the mass of water due to hitting the wall. Okay. What is the decrease in momentum of the wall? So what is the decrease in momentum of the mass of water in A due to hitting the wall? Okay, what is the decrease in horizontal momentum? Okay, sorry, suddenly I have. Yeah, okay, so what is the decrease in horizontal momentum of the mass of water? They are asking you about the horizontal momentum. So let me just clear off something here. Okay, right. You may be thinking that, yeah, when the water hits the wall, it will run down. There's a velocity, right? But this velocity is vertical, okay? When your water was moving, it was initially in the horizontal direction, okay? It was initially in the horizontal direction with a velocity of 5 meters per second. Once it hits the wall, from here to here, your velocity horizontal here is going to be 0. Okay. So they want you to consider the horizontal momentum between here and here upon hitting the wall. Just note that upon hitting the wall, your horizontal velocity is going to be 0. Because you see here, they say horizontal momentum, right? You have to consider only the horizontal component of things, all right? You consider initial horizontal velocity and the final horizontal velocity. So they want the change, or rather the decrease in horizontal momentum of the mass of water. You can just say that change in momentum is mass times, it's basically mv minus mu lah, if you wanted to, or mu minus mv lah. Okay, no, I don't want lah. Mu minus mv is 1.2 times with 1.6 minus 0. 1.2 times 1.6, you're going to get 1.92 Newton seconds. This should be your answer, if I'm not mistaken. Oh, wait, no, I'm mistaken. This is 1. Oh, sorry, wrong velocity. It should be 5, right? Okay, sorry, my mistake. I used 1.6. That one is time. This one is 5.0. So 1.2 times 5 is going to be 6.0 Newton second. Okay, 6.0 Newton seconds. Okay, so this one is correct. All right. Then after that, the next part, find out the magnitude of the same horizontal force that is exerted by the water on the wall. Magnitude of the same horizontal force. So force is rate of change of momentum. So you just check the change in momentum that you had before, divide by 1.6. Okay, because I use 1.6 because that was the mass of water that was involved. Right? The change in momentum that I found here involved the 1.2 kg mass of water, right? So that one involved a time of 1.6. So I'm using that same time here. 6 divided by 1.6, you're going to get 3.75 Newton. Okay, so this one is 3.75 Newton. Right, change out to 2SF is 3.8 lah. Okay, so no issues here. Okay, so straightforward. Then after that, they ask you, state and explain the magnitude of the horizontal force exerted on the wall by the water. Oh, okay. The question before this, they ask you what is the magnitude of horizontal force exerted on the water by the wall. Okay. Then the next one, they say magnitude of horizontal force exerted on the wall by water. Basically, it says this now. If this is the wall, and then say this one was the water, your water will exert a force onto the wall. Your wall will in turn exert a force back onto the water. This one here will be equal and opposite due to Newton's third law. Right? So you can actually just say the same thing. Newton's third law applies, so it will be 3.8 Newton. Right? Because they ask you to state and explain the magnitude. According to Newton's third law, the forces should be equal opposite, so the force is 3.8 Newton. I can probably just write this now. According to Newton's third law, the force on wall by water is equal and opposite to force on water by wall. Therefore, it is 3.8 Newton. This one is one way of explaining it properly now. According to Newton's third law, the force on the wall by water will be equal opposite to force on water by wall. Therefore, it's 3.8 Newton. Okay, so that one is okay. Then lastly, they just ask you to calculate the pressure exerted by the wall on the water. So pressure is actually just force over area. Your force, you already found it as 3.8. I'm using the marking scheme answer at 2SF. Your area, you also have the area at 1.5 times 10 power minus 4. Okay. You have 1.5 times 10 power minus 4. You're going to get a pressure as 2.53 times 10 power 4. Let's go. Let's check the answer. You had 2.5 times 10 power 4. Correct? All right. So under 7 marks from here. Okay, so let's look at page 12 of your February March paper, question 5. All right. So question 1 to 4, this one is actually been done at a separate lesson. That one, the lesson recording for that, I'll upload it for you guys to watch. later on. All right, so we'll continue on from question 5 because this one is something that I have not done for any of the classes that I have. Right, so state conditions required for the formation of stationary wave. This one is just asking you for the general definition of stationary wave formation. So it talks about general definition of formation of stationary waves. I mentioned to you guys before that you can probably use this definition. This one was under page 18 of my notes. This one will, if you want to talk about formation of stationary waves, you can just say that stationary waves are produced when two progressive waves of the same type and equal frequency overlap when traveling in opposite directions at the same speed. Okay, but we can also double check with the marking scheme to see what they want. So in our case here, if you want to talk about formation of stationary waves, you just need to say waves traveling in opposite directions with the same frequency and wavelength. And that's the two most important things they want to see. Waves must travel in opposite directions and they have same frequency and, sorry, the most important thing was waves traveling in opposite directions overlapping and they have same frequency or wavelength. You saying that they have same speed or of the same type, this one is actually not credited. It's optional to put in and it's not credited. The one that is credited is you talking about waves traveling in opposite directions overlapping with the same frequency. If you say frequency already, you don't need to say wavelength. Okay, you don't need to say both. You just need to say either one. Okay, so you want to, you can just memorize this definition from the notes. No? This one will be applicable for any stationary wave formation questions. Okay, stationary waves are produced when two progressive waves of the same type and equal frequency overlap when traveling in opposite directions at the same speed. Basically, the most important one was this underlying sentence here. Okay, so this one is okay. You can copy it from your notes. All right. Okay. So state the phase difference between any two vibrating particles in a stationary wave between two adjacent nodes. Okay, so this one, they're asking you to state the phase difference between two vibrating particles in a stationary wave between two adjacent nodes. So this one, if you're talking about a stationary wave that looks like this, your nodes will be these points here. Okay, the nodes will be these points here. Okay, so the keyword was between two adjacent nodes. It could be this two. This one is what you would say adjacent nodes. Okay, so they say any two particles between any two particles between two adjacent nodes. So if let's say I draw the equilibrium line here, any two particles between these two nodes, what is the phase difference between them? So I explained to you guys before that the phase difference should actually just be 0 degrees. Okay. So again, you can also find it from the notes I mentioned to you guys before. Particles between adjacent nodes will also always oscillate in phase with one another with a phase difference of 0 degrees. It's only when you're talking about particles in adjacent loops or opposite sides of a node that you have vibration out of phase or vibration 180 degrees out of phase. Okay, so this is one thing you can see from here. All right, this is from your notes also. Okay, so that one is okay. Then after that, you have a motorcycle that is traveling at 13 meters per second along a straight road. The rider of the motorcycle sees the pedestrian standing in the road directly ahead and operates a horn to emit a warning sound. The pedestrian hears the warning sound from the horn at a frequency of 543 Hz. The speed of the sound in the air is 334 meters per second. Calculate the frequency to three significant figures Okay, so this time the question specifically mentioned to you how many accept to use of the sound emitted by the horn. Okay, so in my case here, your pedestrian is this person here. Okay, and then you have a motorcycle that is traveling towards the pedestrian. Okay, this is a motorcycle. All right, so the motorcycle sees the rider of the motorcycle sees a pedestrian standing in the road directly ahead. Okay, so your motorcycle is moving towards the observer. The pedestrian hears the warning sound from the horn at the frequency of 540 Hz. This one is your observed frequency. The speed of sound in the air is 334 meters per second. This is your speed of your wave. Okay. Then the motorcycle is traveling at 30 meters per second. This one is speed of your source. So your motorcycle is traveling at 13 meters per second. He is emitting sound waves from the horn to warn the pedestrian. That one was at a frequency, sorry, that one is at a certain frequency of the source, which we do not know. Okay, the frequency of the observer was, the frequency observed by the observer is 543 Hertz. The speed of my wave is 334 meters per second. So in my case, this one is pretty straightforward. You are moving towards the observer. Okay, you're moving towards the observer. This one will mean your F0 is more than your Fs, your source frequency. So observed frequency would be VW over VW minus Vs times Fs. This is something that you guys would have remembered from your wave chapter. Sorry, I accidentally deleted the screen share. Okay, so never mind. I'll calculate the frequency to 3 centimeter figures of the sound emitted by the horn. This one I know that F0 is VW minus Vs times Fs. Fs is what I want to find. Okay, but I know everything else. So you just sum in the values. 543 equals to 13, sorry, speed of the wave, right? This one is 334 over 334 minus 13 times with Fs. Okay, so right now Fs will be basically what you have there. 334 minus 13, 334 divided by that, 543 divided by the answer. You're going to get the answer as 522 Hertz. Okay. This one was the answer, no? 522 Hertz. Okay, so this one, frequency observed, frequency of the source is 522 Hertz. All right, then after that, if you look at the second part, they tell you the motorcycle rider passes the stationary pedestrian and then moves directly away from the rider, from her. As the rider moves away, he operates the horn a second time. The pedestrian now hears sound of increasing frequency. State the variation, if any, of the speed of the motorcycle when the rider operates the horn for the second time. Okay, now this one is the one that may cause you guys some confusion. The first thing that you guys would have learned last time was this. I mentioned to you guys before that it is moving towards observer, your frequency observed is more than your source frequency. Basically, what you perceive is that basically what is happening here is that observed frequency is higher than your source frequency. But then on the other hand, when you're moving away from the observer, your observed frequency will be less than your source frequency. Basically, your observed frequency is lower than your source frequency. This is what we mentioned. Now, the thing here that you will also need to know is that the frequency change, the frequency change either increase or decrease depends on speed of the source. Okay, so in my case here, I already know that the rider is moving away from the observer, the pedestrian here. So right now the rider moves away, he sounds the horn for another time, but what the pedestrian hears is that the sound is increasing in frequency. So what they're asking you right now is, what's the speed of the motorcycle rider when he operates the horn for the second time? What is basically happening here is that if I try to draw you a graph of observed frequency versus time, because your source is moving away, I know that observed frequency will always be less than source frequency. Let's just say that the x-axis here is my source frequency. My observed frequency will always be less than the source frequency, but at the same time, I notice that the observed frequency is increasing. So what you're basically seeing here is something like this. Your observed frequency is always less than your source frequency, which is your x-axis here. But then the decrease is getting less and less and less and less. Okay, that's why you perceive your observed frequency as increasing. I mean, if I draw this line like this, you're perceiving your observed frequency to be increasing, but it's still less than, this one, your observed frequency is increasing, but is still less than Fs. It's still less than your source frequency. Okay, so in my case, because my source frequency, my observed frequency is seen to increase right now, I can actually say that the source is slowing down. Okay, back to what I mentioned here. I told you frequency change depends on, which is either an increase or decrease, depends on the speed of the source, right? So what you should know from here is that the larger the speed, the greater the change, and vice versa. Okay, if you are moving with a larger speed, your frequency change is greater. The greater the frequency change. Wait, sorry. Okay, if you're moving with a larger speed, your frequency change is larger. If you're moving with a lower speed, your frequency change is lower. Okay, it is something related to what I explained to you guys before in your waves notes, on the Doppler effect. Let me just find out that little diagram there. A-level AS notes, revise. Yes, this part here. Remember the last page here of your notes. I remember explaining to you what's the effect of your frequency increase or frequency drop when you are speeding up or slowing down, right? So just know that your frequency change, which can be either an increase or decrease, depends on the speed of your source. If your frequency change is large, you're moving with a higher speed. If your frequency change is small, you're moving with a lower speed. So right now, you're basically seeing that your observed frequency is getting less, higher and higher and higher and higher. You are actually having you're actually having a large, smaller frequency drop. So that's why here I can say that the source is slowing down because the frequency decrease. Maybe I just write it properly. Because the frequency drop is decreasing. Okay. From here, it drops this much to this much to this much to this much. Maybe this one drop 20 hertz. This one drop minus 10 hertz. This one drop minus 5 hertz. This one drop negative 2.5 hertz. So this is what we mean by the frequency drop. But even if you look at the frequency drop like that, if let's just say I give you the frequency of your source just now as 552 lah. Okay, this one was 552, right? So 552 is going to maybe say, right, say your frequency of your source is 522 hertz. If you're talking about observed frequency, right now what you're probably seeing here is something like this. 502 hertz going to 512 hertz, then going to 518 hertz, and so on and so forth. Okay, so you see this one, my frequency is still less than source frequency, but the frequency observed is increasing. The frequency drop is getting less and less and less. This one minus 20. This one, this one is minus 20 with respect to my original source. This one is minus 10 with respect to this. Okay, so that's what we mean now. So what is the speed of your motorcycle? Simply put, it is slowing down. The speed is decreasing. The motorcyclist is slowing down. The speed is decreasing. Okay. So basically that is what you can see from here. All right. Okay, so this one is okay. Then after that, I move on to the next part. The next part is based on your new addition to your syllabus, the March 2022. Sorry, the next question is based on a new addition to your syllabus, which is polarization. So you have a beam of vertically polarized monochromatic light that is incident normally on a polarizing filter as shown in figure 5.1. The filter is positioned with its transmission axis at an angle of 20 degrees to the vertical. The incident light has an intensity of I0 and the transmitted light has an intensity of IT. By considering the ratio of IT to I0, calculate the ratio of amplitude of transmitted light to amplitude of incident light. Okay, so this little thing here is your polarizing filter. Your transmission axis is this one. What you have is a polarized light incident on a polarizer. So you have a certain intensity going in, and then you have a certain intensity going out. So remember I mentioned to you when you're talking about polarized light that is incident on a polarizer, you would need to use something called Malus's law, which is basically summarized by this equation. I is I naught cos square theta. Remember? So it's basically this little equation here that you would need to use. So if I refer back to this, I know that I is I naught cos square theta. If I go and apply it to the variables that are given in the question, this one will actually be IT I naught cos square theta. Okay, so they want the ratio of amplitude of transmitted light and amplitude of incident light. You can actually do something like this, where you say this, or you also know one thing from before. This one is equation 1. Remember, intensity is proportional to amplitude square. These are the two relations that you need to know. Okay, you gotta write this as equation 1. This is the first relation. This is the second relation. So if IT is I naught cos square theta, IT to I naught is cos square theta. But at the same time, amplitude t square to amplitude O square will be the same as cos square theta. So AT to A naught will be square root of cos square 20, which is basically just going to be cos 20 lah. Okay, cos 20 square is going to be 0.911. Okay, I believe this is the working. Let me just see. Right, you got 0.94 though. Cos 20, sorry, I did the wrong calculation here. Cos square 20 would be 0.94. It's basically cos 20 now, 0.940. 0.940. Okay. This one, you don't need to have the square. This one is just cos 20. Okay. So that is your working for this one. Show your working. Amplitude of transmitter light to amplitude of incident light. This is your working. All right. This is for 3 marks. The workings on the left in green, this is your working for part 1. All right, then after that, you look at the part 2 right now. The filter is now rotated about the direction of the light beam from its starting position as shown in figure 5.1. The direction of rotation is such that the angle of transmission axis to the vertical initially increases. Calculate the minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value that it had when the filter was at its starting position. Okay, so they basically mentioned this to you. Your filter is now rotated about the direction of your light beam from starting position. The direction of rotation is such that the angle of transmission axis from the vertical initially increases. You rotate your angle in such a way that it increases. Find out the minimum angle that the filter must be rotated so that the intensity of your transmitted light returns to the value that it had when the filter was at its starting position. So this one, the answer for this is 140 degrees. Okay, the answer is 140 degrees. But how do you make sense of this? Okay, so basically what we're doing here is this. This one here is your polarizing filter. with its transmission axis like this. Your angle is measured from here, from the vertical. And we know that it's at 20 degrees to give you an intensity of IT. Okay, so right now, what they mention is that you want to rotate your polarizing filter about this beam of light here. So basically your transmission axis will start to tilt to maybe like this, to like this, to like this. Okay, so you start to tilt, but then they're asking you what is the angle that you will need to rotate it about in order to get back the same intensity IT as before. Okay, so that is what the question actually wants you to do right now. How much angle should you rotate it in order to get back the same intensity as before? So I know that I is I naught cos squared theta. In my case, I know that I have something like this. If I try to plot out the graph of I naught versus the intensity versus theta from this part of your notes last time, if let's say I try to draw this one out, what you will have is something that looks like this. So I versus theta, you will get a cos square graph that looks like this. Okay, so at 20 degrees, you're getting something like this. This one is, let me just try and draw it nicely for you. You're gonna get something like this. I draw it longer. If I versus theta, you're gonna get something that looks like this. This is your cos square graph. All right, this one here would be I naught. If your transmission axis is at an angle of 0 degrees, but right now you are at 20 and angle of 20 degrees. This one here would be 90 degrees. Okay, this one here would be at an angle of 90 degrees to give you 0. You are at a certain angle right now at 20 degrees. At 20 degrees, this is where you're getting your IT. So basically what you're doing now is that you're trying to rotate your angle, theta, until you get back the same IT. Okay, this is your angle that you want to find. Okay, so how do you get the answer? If you see from here, this one would be 90 plus 20. This one should be the answer was 140 though. Okay, this one the answer is angle of 140 degrees. So how am I going to get that answer? Just like this one. If this one is 20 degrees, this part here would be 60. You see, the thing now would be that if this one is 20 degrees, this part will be 19 minus 70. This one here will be 70 degrees. This part here will be 20 degrees. But then from here to here, this one is 140 degrees. I want to get back that same intensity IT here. Okay, so how do I get back that same value? If I try to get plus 70 from 90, I'm getting 160. This one cannot be. The answer is 140. So how do I get the 140? The angle is 140 degrees. So there could be something here that I'm missing out. You know, and the angle of 20 degrees to the vertical. Calculate the minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value that it had when the filter is at its starting position. So right now the angle is at 1%. So the angle is at 140. Allow answer of 40 degrees. Filter rotated in opposite direction. Okay, right. This one, just leave this one for now. This one I'll have to have a proper look at this one to tell you why the answer is 140. Because from what I can see from the graph here, I'm getting 90 plus 70 giving me 160, but the actual answer is 140. There could be some calculation that I need to do from here. Okay, so for this one, just leave it for now. All right. The next lesson, I will probably have to re-explain this one. Okay, right. Under the February-March 2022 paper, the structure question that we did last week, under the topic of polarization, there was one small part that I did not manage to sort out with you last week. Okay, so let's revisit that question for a little. Right, so the question was that they told you that you have a beam or polarized, you have a beam of vertically polarized monochromatic light that's incident normally on a polarizing filter, as shown in the figure here. So the filter is positioned with its transmission axis. Transmission axis refers to this thing here, all right, that is placed at an angle of 20 degrees to the vertical. The incident light has an incident intensity of I naught, and the transmitted light has an intensity of IT. So when you have a vertical polarized light that is incident on this polarizer here, it originally had an intensity of I naught, and then after passing through the polarizer, it had an intensity of IT. Okay, so we went through part one, which deals with finding the ratio of the amplitude of transmitted light to incident light. And then after that, the second part was what we wanted to answer. So this part here, it was mentioned that the filter is now rotated about the direction of the light beam from its starting position shown in the figure. All right. The direction of rotation is such that the angle of transmission axis to the vertical initially increases. They told us the direction of rotation is such that the angle of transmission axis to the vertical initially increases. Calculate the minimum angle through which the filter must be rotated so that the intensity of transmitted light returns to the value that it had when the filter was at the starting position, right? So the key thing here to note was that they want to rotate the polarizer until the intensity of the transmitted light is back at the value that it had when the filter was at its starting position. So looking at this diagram here, what you're supposed to do is that your polarizer, you're supposed to rotate it. So if you were originally at this position for your polarizer with its transmission axis like this, you have an intensity of IT. So you're supposed to rotate your polarizer until at a certain angle, you're getting back an intensity of IT after passing through the polarizer. So the angle that you want is in a way this angle theta here. Okay, so that time I mentioned to you, when it comes to polarized light that is incident on a polarizer, we have something known as Malus law that tells us the intensity before and after passing the polarizer. That one is given by this equation. Because we see that there's a cos square function here, if we were to plot a graph of intensity versus theta, we know we're going to get a cos square graph, which looks like the blue color line that we have here. Now, at the angle of 20 degrees from the vertical, which is this one here, we're supposed to have an intensity of IT. So the question says that we are supposed to rotate this polarizer so such that the angle increases until we are getting back an intensity that is the same as that before. So from here, you can see from here, if you are trying to get back the same intensity, if you try to extrapolate the graph, the new angle would be right over here, okay? So that time I mentioned to you, if this one is 20 degrees, this one by right would be 70 degrees. And then because you see that this part and this part are kind of symmetrical with each other, you can actually translate the angle over, where right now you can say that this part here is also 70, and then after that this one obviously is going to be 180, and then this one will be 20. Now of interest to you is that time I mentioned to you the angle that I measure by right will be 90 plus with 70, giving me 160 degrees. The angle that I got was 160 degrees, but the answer was actually 140 degrees. Okay, so that was where the thing started to become a bit confusing. How come I'm getting 140 degrees for the answer? Okay, there was nothing wrong with the diagram and the understanding from there. It's just that I overlooked something when reading the question. You see, they say minimum angle through which the filter must be rotated so that the intensity of the transmitted light returns to the value it had when the filter was at its starting position. Okay, when the filter is at starting position, theta is not 0. Theta was actually 20 degrees. Okay, you are trying to measure the angle at which you have turned the polarizer from the starting position. Okay, your starting position is actually right here, 20 degrees from the vertical. Okay, so if you want to measure the angle, it will be from here to here. All right, so you are not referencing your starting position from the 0 degree side. Instead, you're referencing it from the 20 degree side. Okay, so in my case, with that in mind, this one will be my start. And then this one would have been my end. Okay, so from here to here, it would actually be 140. Because you see from here, 20 plus with 70, sorry, 20 plus, okay. You can see from here, this is 20. This one here, I mentioned to you is 160. So from 20 to 160 is just 160 minus 20, giving you 140 degrees. So that's why the answer was 140 degrees, because your starting position is measured not from the vertical, but from the 20 degree angle. Then you measure up to the 160 degree angle. The angle you have turned is actually 140. Okay, so it's really a matter of realizing that your starting position is not from the vertical, it's not from the 0 degrees, instead it's from the 20 degree angle. Okay, so this one should be okay. Okay, just look at question 6, the next one. They tell you the ends of a metal resistance wire are connected to a battery of EMFs 8 volts and negligible internal resistance, as shown in figure 6.1. The power dissipated by the resistance wire is 36 watts. Find out the current in the resistance wire. Okay, so this one should be very straightforward. Power dissipated by the resistance wire, which is this one, is 36 watts. So find out the current. P is I square. Do I need to use I square? No, P is equals to VI. Because you can see from here, you have the resistance wire connected to a battery of EMF 8 volts and negligible internal resistance. There is no internal resistance here. So by applying Kirchhoff's second law for this part itself, you will be able to know that this one is going to be 8 volts. Okay, so power is 36, voltage is 8. Find out my current. This one will be 36 divided by 8, giving me 4.5 ampere. Okay, so this one is my current. It will be 4.5 amps. So this one is quite straightforward, 4.5 amps. Then after that, we go on to the next one. Find out the number of free electrons that passes through the resistance wire in a time of 50 seconds. Number of free electrons. So I know is 4.5 amps. This one I make use of this value here. So they want the number of free electrons that passes through the wire in a time of 50 seconds. I is rate of flow of charge, but this one Q is total charge. It's actually number of charged particles times the charge of one charged particle, giving me this. Okay, so I was 4.5. Number of charged particles or free electron is 1. The charge of an electron is 1.6 times 10 power minus 19 divided by 50, and would be 4.5 times 5. Sorry, 4.5 times 50 divided by 1.6 divided by 10 power minus 19. You're going to get 1.41 times 10 power 21. Okay, so this is your other answer. 1.41 times 10 power 21. Okay, so that one is okay. And then next, find out the resistance of your wire. Okay, 1.41 times 10 power 21. So find out the resistance of your wire. This one shouldn't be that difficult. Resistance of the resistance wire, you can actually just use P equals to V squared over R. Your power is 36, your voltage is 8. You can find out your resistance easily. So R is 64 divided by 36. It's going to give you 1.78 ohms, if I'm not mistaken. Yeah, you're going to get 1.8 ohms as your answer. But you can just use P equal, you can just use more SF, 1.78 ohms. So this one R is 1.78 ohms. Okay, then after that, they tell you the metal of the resistance wire in the circuit has a resistivity of 1.4 times 10 power minus 6 ohm meter. The cross-sectional area of the wire is 0.25 millimeter square. Determine the length of the wire. So as I mentioned to you before, whenever you hear mention of resistivity and then you hear mention of length, the thing that you should just use is just going to be R equals to rho L over A. Your cross-sectional area is given directly. You don't need to change it to pi over 4d square. So you can just use it straight. So length of the wire, just sum in your values. Your resistance is 1.78. Your resistivity is 1.4 times 10 power minus 6. Length is what you want to find. Your cross-sectional area is 0.25, but millimeter square. So this one is 10 power minus 3 times 2. Okay, 1 millimeter square is the same as 1 millimeter square like this. 10 power 3 meter square. 10 power minus 6 meter square. Okay, maybe I just write it as this now. Okay, this one is you changing it to meter square. So eventually your value of L would be 1.78 times 0.25 times 10 power minus 6 divided by 1.4 divided by 10 power minus 6. You are going to get L as 0.318 meter, if I'm not mistaken. Yes, 0.32 meter. This is in 2SF. I already in 3SF is 0.318 meter. Okay, so this one L is 0.318 meter. Okay, so now in part C, they tell you the circuit shown in figure 6.1 is modified by replacing the resistance wire, by replacing the original resistance wire with a second resistance wire. The second wire has greater diameter than original wire. There are no other differences between the second wire and the original wire. So the only thing different here is greater diameter. Now, by reference to your resistance, state and explain whether the power dissipated by the second wire is more than, less than, or same as the power dissipated by the original wire. Okay, so for our case here, we know that R is rho L over A, but then A is pi over 4D square. They say everything else is the same, only the diameter is greater. So I can actually say that rho and L constant, rho and L is constant, therefore R is inversely proportional to diameter square. All right, so if diameter is greater, the resistance is therefore smaller. Okay, so that is what we know. Okay, then after that, we know one thing, power is VI. V remains constant here because remember just now the way that the diagram was drawn was something like this. There are no internal resistances. Your resistance wire is just this. So if let's just say you have an EMF of say 8 volts, this one will always be 8 volts. You can change it from wire 1 to wire 2. The PD remains the same because of Kirchhoff's second law. All right. So in my case, I would say V is constant. Therefore, P is proportional to I. Okay. So what are the things that I can say here? If R drop, I increases. Therefore, P will increase. My power dissipated should actually be more. No, power remains the same. Wait a minute. Oh, sorry. Oh, sorry. I'm looking at C, right? I was looking at D. We know that you have less resistance. They say less potential difference. Sorry, same potential difference, so more power dissipated. Okay, this one I was basing it on this, on P equals to VI. This one is what I did now. But there's another way to look at it. This one is based on the other answer choice. This one I'll just draw it here. Rather than using P equals to VI, you can have actually used P equals to V square over R. This one is actually better. If I know that V is constant, P is inversely proportional to R. So if R drops, P increases. Yeah, this one is actually the better one. Okay. The one that I just did in yellow over here, if you use P equals to VI, you would actually still get back the same answer lah. But this one is a bit more tedious. It will be better if you were to tie it with the ones that is in pink here. This one is actually a lot easier to see because there's a direct relation between my power and my resistance here. Okay, my V I know is constant. All right. Now you may be wondering why is it that I can also use I square R, but then it will still give me that same kind of working where it's a bit tedious, right? You can also still use P equals to I square R if you wanted to, All right, you can use P equals to I square R, you can use P equals to VI, but those are a bit tedious, so I won't recommend that you use this. Instead, please use the one at the top, P equals to V square over R. It will make your life a lot easier. Okay, right, then after that, you look at the other part. There's another part to this question, this one under question D. All right, okay, so question D, they tell you the circuit shown in figure 6.1 is modified by connecting a second battery of EMF 8 volts and negligible resistance in parallel with the original battery and the original resistance wire. By reference to the current in the resistance wire, state and explain whether the addition of a second battery causes the original resistance, causes the power dissipated in the original resistance wire to decrease, increase, or stay the same. Okay, this one probably relates to what I mentioned to you guys before. You see, if I have two batteries that are connected in parallel like this, in the last lesson I mentioned to you, if batteries are connected in parallel, it's actually going to be the same as 8 volts only in my case. So this one, my equivalent circuit, is just going to be something like this. This is my resistance wire. My battery has an equivalent resistance, equivalent EMF of just 8 volts. All right. So there's actually no change from the original diagram. Okay. So in my case, what I will probably be able to say here is that current in the wire is PD is the same, current is the same. They say with reference to current, is it? Oh, okay. Here they say with reference to current in the resistance wire. Okay, they say with reference to the current in the resistance wire. This one is still resistance R as before. This one is still PD of 8V as before. When you're talking about your current, it is still the same. Okay, so that's why the answer say here, current in wire is still the same, therefore power remains the same. Okay, because in my case, let me just rewrite this properly for you. P is equals to I square R, right? Let's just do P is equals to I square R, or P equals to VI now. I think I better just use P equals to VI. Okay, so V and I remain the same, thus power remains the same. You can also explain it using P equals to I square R, where you say that R and I remain the same, thus power remains the same. Okay, but whatever your answer that you use, you must make it with respect to your current. You must mention current because the question says by reference to current. So your answer must relate to your current here. That's why here I cannot just say I want to use P equals to V squared over R. If I use this, there's no current term to use. So I won't use this. Instead, I'll use P equals to VI or P equals to I squared R. All right. Okay, so that is for this one. This one is battery connected in parallel. It will just give me this one. Okay, this is something that I mentioned to you guys last week before. For battery connected in parallel, your EMF won't change. So because your battery is connected like this, is still going to have an equivalent EMF of 8 volts. So your overall circuit is still the same as before. Okay, right. So this one is DC circuits. And then we also have one last question from this paper. That one was your particle physics. I'm just going to clear off everything here first. Okay, right. For this one, I think most of the stuff should be okay, except I've got one part where it was not covered in my notes. Right, so let's go through this. You have a nucleus of sodium-22 that decays by emitting a beta plus particle. A different nucleus is formed by the decay. State the name of another lepton that is produced by the decay. So if we know that this one is beta plus decay, we know that this one is positron. It starts with P. This one is already giving you a hint that it is proton. Proton change to neutron, giving you beta plus. Plus is neutrino. Okay, so this one is 0, 1, 1, 1. So state the name of another lepton that is produced by the decay. We know that this one and this one are your leptons. Okay, this one was positron. This one was your electron, neutrino. Okay, so the answer for this was electron, neutrino. Okay, so one thing I also mentioned to you last time is that there's something like a pattern here where you see that positron is an antimatter particle, it's an antiparticle, this is antimatter, this one should be matter. All right. Okay, then the second part of the question, we ask you, find out the nuclear number and proton number of the nucleus that is formed by the decay. This one, you will have to use this. You need to look at the actual decay process here where we tell you sodium 22 11 decays by beta plus particle emission to give you some unknown nucleus, right? Let's just say the nucleus is X plus beta particle. All right. So in my case, I want to balance the proton number and the nuclear number. This one here will be 11 minus 1, giving me 10. This is 11 minus 1. And then this one will be 22 minus 0, giving me 22. So therefore, your nuclear number is 22. Your proton number is 10. Okay. Let me just double check for you. Yes, it's 22 and 10. All right, just like that. Okay. All right, then after that, we mentioned that the quark composition of a nucleon in sodium-22 is changed during the decay. Describe the change to the quark composition of the nucleon. All right, so looking at what they're saying here, the quark composition of a nucleon in sodium-22 nucleus is changed during the decay. Your nucleon is either a proton or neutron. So they're saying that one of these inside your sodium nucleus has actually changed. What was the change in their quark composition? So you know that we are talking about beta plus decay. A proton actually changed to a neutron. So in our case, we know that proton, the quark composition was up, up, down. Neutron is up, down, down. What has actually changed is that up changed to down. So you have actually written it as something like this, where you can either say up quark changes to down quark, or you could just say up, up, down changes to up, down, down. That was what the marking scheme said, if I'm not mistaken. Up, up, down changes to up, down, down, or up changes to down, whichever you want. Okay. Yeah, whichever is more sensible for you. Okay, then after that, the last part, we mentioned to you this thing. where a baryon consists of quarks that are of the same flavor. The charge of the baryon is -2e, where E is the elementary charge. Calculate in terms of E the charge of each of those quarks. Okay, now this one here is where they start to ask something a bit different. This one wasn't inside my notes. The one that was inside my notes was that I mentioned to you guys that hadron is actually groups of quarks. Okay. It's actually groups of quarks. This is in general. Okay. There is also something called baryon. Okay. It's also considered to be a quark, but it's actually a more specific hadron, where we tell you that it is actually group of 3 quarks. Okay, baryon is considered as group of 3 quarks. Okay, it's also group of quarks, but it's more specific in the sense that it tells you how many quarks do you need to have. In our case, baryon is group of 3 quarks. Okay, this is a more specific example of a hadron. So in our case, they tell you the baryon consists of quarks that are of the same flavor. So these 3 quarks have exactly the same quark type, and they all add up to give you -2e. So in my case, if I wanted to find out the values of these quarks, what I'll do is that you will do something like this, where you say that x plus, okay, maybe not x, maybe I put q to denote the charge. Q plus q plus q equals to -2e. So this one is q, 3q equals to -2e. And then from here, q is -2/3e. Okay, so this one is your charge, -2/3e. But then after that, the next question will ask you, what is a possible flavor or type for this quark? So if you refer back to the tables that you have in the particle physics notes, there was a table that summarized to you the quark compositions, the type of quarks that you have. So from here, there are some things that you can see. Okay, maybe I just use the short form of it. Okay, if you look at the top part here, this one here, the table is telling you the types of quarks that you have, the 6 types of quarks that you have. So in my case, up, charm, top would have a charge of +2/3e. But your charge right now is not +2/3e. Your charge is -2/3e. Okay, needless to say, you don't need to consider the bottom row because the magnitude is also not even the same as 2/3. This one was 1/3. So you don't really need to consider the bottom one. You consider the top one, all right? So you consider the top one, in order to have a charge of negative, the only difference between this and this was the fact that the sign is different, isn't it? So how are you going to get a -2/3e? This one is if you're talking about the antimatter particles, the antiparticles. So you need to have up quark, charm quark, and sorry, anti-up quark, anti-charm quark, anti-top quark. Basically, you need to have anti-up quark, anti-charm quark, or anti-top quark. Okay, to get a charge of -2/3e, you need to talk about the antiparticles. Antiparticles always has opposite charge. Okay, always opposite charge, but same magnitude lah. All right, so I have magnitude 2/3e. I just need to have them in an opposite charge, opposite sign. I need to talk about the antiparticles. So in my case, what are the possible flavors? You be anti-up quark, anti-charm quark, or anti-top quark. So you can either write it as this, no? Anti-up, anti-charm, or anti-top. All right. Okay, you can also write it other ways now. You can also write it as up anti-quark, charm anti-quark, top anti-quark, or you can even give them in symbols. Anyone would do. All right. Okay, so this one is okay.